Hello everyone, welcome once again to our session for today. We'll continue our discussion on our topic on maxima and minima, that is optimization problems. Alright, so last time we talked about the concept on how to solve optimization problems. Now we will use the concept that we have learned from our previous discussion on the extreme value theorem, so that we can also apply the concept in this topic class. Okay, so we have here our example number 1. So a closed box with a square base is to have a volume of 2000 cubic inch. The material for the top and the bottom of the box is to cost 3 cents per square inch, and the material for the sides is to cost 1.5 cents per square inch. Determine the dimensions, or determine the dimension of the box so the total cost of the material is least. Okay, so to solve this problem, we will use the procedure that we have learned in our previous session about this topic. So we have to begin by deciding precisely what we want to optimize. So in this case, we are going to optimize the total cost. So because total cost of the material is least, so we are going to optimize the cost. Okay, so before we solve this problem, let us write down first the given, so it will help us in the process of solving this problem. So we're given in this problem, the problem says that closed box is to have a volume of 2000 cubic inch. So volume is given as 2000 cubic inch. And then in terms of cost, so the top and bottom is to cost 3 cents per square inch. So the top, so the cost for the top, the cost of the materials for the top is 3 cents. 3 cents per square inch. The same with the bottom, or for the bottom. So this is also 3 cents per square inch. And for the sides, so the cost is 1.5. Now 1.5 cents per square inch. Okay, and we are asked to determine the dimension. So this problem required us to solve the dimension. Okay, so as mentioned in our previous video about this topic, so one of the strategy here is to make a presentation of the box of a certain material or whatever is mentioned in the problem. So in this case, closed box is mentioned, so we have to make an illustration of the box showing the dimension. Okay, so assuming this is our box, so it's mentioned in the problem class that the base is a square. So what does it mean? So we have a square base. So this is the base of the box. Okay, so this is the base of the box. So since this is a square base, so we can let this side of this box equal to x. If this is equal to x, this is also x. Alright, and since it didn't mention that this is a cubic box, so we cannot assume the value here as x, so it should be a different dimension. So we can represent this by h. And since we are talking of cost, so we are going to make an expression of total cost, or simply cost, as a function of the given variable, no, in our illustration. So cost, since our illustration here contains two variables, so we have to express our cost as a function of our variables here, which are x and h, equal to, so the cost is dependent on the given cost of the material, which is for the top and bottom, that is 3 cents per square inch. So the unit is in cents per square inch. So when we're talking of cost, so that the final unit will be in terms of cents. So the inch there, the square inch, will be gone, or will be eliminated, because we have inch squared at the numerator, we have inch squared at the denominator. So inch squared divided by inch squared, so that becomes 1. So the remaining unit will be in cents. So the cost should be in that unit. Alright, so it means that we're talking of area here. Area multiplied by area, because the area is in terms of inch squared, and cost is in terms of cents per square inch. So it means that we are going to multiply the area, no, for the bottom, or we can start at the top, whichever one. You can start with the cost for the bottom or top. Anyway, we have to add them up. So area at the bottom, we have, or it's better to be consistent with our problem, so we start with the top. So here we have this length equal to x. Since this line, or this side, is just parallel to this side, so this is also equal to x. Alright, and this side here, since this is parallel to this side, so if this is x, this is also x here. Okay, so now for the top, so area of the top is just the product of length and width, so we have x squared. Okay, then multiply this by the cost, which is 3 cents per square inch, then plus at the bottom, so the bottom is also a square, so we have the area there is x times x, so that is x squared, then multiplied by the cost, that is 3 cents also per square inch, then plus sides. So the side, what are the dimension of the side? We have this x and h. Okay, so when you multiply this x and h, we get the area of the side. Alright, so area of the side is just the product of x and h. Okay, and the cost of the side is 1.5, no, 1.5 cents per square inch. So we have to multiply this by 1.5. Okay, this is 1.5. Then since there are 4 sides, so we have to multiply this by 4. Okay, so our cost function now, function of x and h, is equal to, you just combine this one, similar terms. So 3x squared plus 3x squared is 6x squared. Then plus 4 times 1.5, so that is also 6 multiplied by x times h. We can call this equation as our equation 1. Okay, and then as much as possible, class, we have to express the cost in terms of a single variable. So now we have the cost C as a function of 2 variables, x and h. So we have to express either x in terms of h or h in terms of x, so that the cost will be a function of a single variable. Alright, now we have, so how to express h in terms of x or x in terms of h? So the only way is to use this concept of the volume. So when we speak of box, so we have a volume, which is simply the product of the length, width, and height. So this is the general formula of the volume of a box: length times width times height. So in our illustration, so our volume is equal to, the length here is equal to x, the width is equal to x also, and the height is equal to h. So therefore the volume is equal to x times x is x squared, then multiplied by h. But in the problem, we're given volume, or the cubic box, the box is to have a volume of 2000 cubic inch. So by the way, our box is not a cubic box, so it has a square base. Okay, so from this given, we can use this, substitute this to our equation of the volume. So we have V here. V is given as 2000. So 2000 equal to x squared times h. Then from this, we can solve for h. So divide both sides by x squared. So we have therefore 2000. H is equal to 2000 divided by x squared. So we can call this equation as our equation 2. Alright, then substituting equation 2 in equation 1, substituting equation 2 in 1, so our equation becomes, I will write the right side first. We have 6x squared plus 6x times. So instead of writing h, so since h is equal to 2000 divided by x squared, so we can rewrite this instead of h. So h is equal to 2000 divided by x squared. Okay, so if you look at the right side of the equation now, so there are only one variable, which is the x. Okay, so now our cost is a function of a single variable. It's no longer a function of x and h, but only x, because on the right side we have only one variable here, which is x. So unlike in our previous equation, so before the substitution happens, so we have here on the right side we have x and h, so our cost is a function of two variables. But now since we express h in terms of x and substitute to equation 1, so our cost function now is a function of a single variable, which is x. Okay, and we can divide. We have x at the numerator, we also have x at the denominator, so therefore our cost function now becomes 6x squared, then plus 6 times 2000. Okay, so we have here 6 times 2000, so we have 12,000. Divided by, so x divided by x squared, so x divided by x squared, so we have at the denominator x. Or we can rewrite this as 6x squared plus 12,000 x to the negative 1. Okay, so since we are optimizing this problem, the total cost is to be minimum or least. Okay, as mentioned here, total cost of the materials should be least or minimum. So we are optimizing here, so we are going to use the concept of the extreme value theorem, where we have to set the first derivative equal to 0 to determine the maximum or minimum value. Alright, so in this case, to determine the minimum total cost of making the said closed box with a volume of 2000 cubic inch. Okay, so differentiating, both sides with respect to x, so we have the derivative of the cost as a function of x with respect to x equal to, so this is applying the rule in differentiation, so this becomes 12, this becomes 12x, then power rule applied here, so the exponent negative will go down, multiplied by 12,000, so this becomes negative 12,000 times x to the negative 1 minus 1, so this will be negative 2. Okay, so for optimization, so we have to set this equal to 0. So to find the minimum or maximum, so we have to set the derivative equal to 0. So therefore we have 0 equal to 12x minus 12,000 so we can bring this down, okay, and this becomes positive. Okay, then solving for x, so to solve for x, so we need to move this to the other side, so transposing that to the other side, so we have, so this becomes positive, so we have 12,000 divided by x squared equal to 12x. Then multiplying both sides by x squared, So we have 12,000. So we multiply this by x squared, so x squared divided by x squared, so it becomes 1. So what is left in the left side is 12,000 equal to, so this will be 12x cubed. We multiply this also by x squared, so this becomes 12x cubed. Now if we are going to solve for x, so first we need to divide both sides by 12. Okay, so divide this by 12. So 12x cubed, divide this also by 12. So 12,000 divided by 12, that is 1,000, equal to 12x cubed divided by 12, so that is x cubed. So from here, we can solve for x. So to solve for x, you just take cube root on both sides. So taking cube root on both sides, okay, so cube root of 1,000 and cube root of x cubed. So we have 10 equal to x. So therefore our x is equal to 10, sorry, this is 10 inches. Okay, now after solving for the x, we can solve for h, because we are asked to solve for the dimension, which is this one, and also this one. So substitute this x equal to 10 in our equation 2. Okay, so solving for h, so we have to substitute x equal to 10 in our equation 2. Alright, so what is our equation 2? So our equation 2, so in our equation 2, we have h equal to 2,000. Sorry, this is yes, that's 2,000. So 2,000 divided by x squared. So substituting the value of x, so 2,000 divided by x, which is 10, then you square this. So h is equal to 2,000 divided by 100, or h is equal to 20. Okay, so 20 inches. Alright, so we have solved x and h, and we can now conclude, no, that the dimensions, so the dimension of the closed box, so how will we see it? So therefore, the dimension of the box that will give least total cost is, so we have the length, which is 10, that is 10 inches by, so the width is also x, that is 10 inches by, so the height h is equal to 20, so by 20 inches. Okay, so this is our final answer, class. So the 10 here, so ito yung x natin, no, from our box, that is the length, and this is our width, this is also x, and 20 inch or 20 inches, so this is the h. Okay, so I hope you have understood our discussion and the solution of this problem. Okay, and please kindly solve the rest of the exercises that you can see in our PowerPoint. Okay, thank you very much, class. Stay safe and healthy always. God bless. Bye.